Good afternoon, everyone. So, today I want to give you one numerical problem. So, all of you note down it. Today, we are going to discuss one numerical problem and Stokes law. Numerical problem, all of you write down it. Keep your pen and paper ready and write down. Okay. The problem is about Hazen-Poiseuille's equation, okay, related to Hazen-Poiseuille's equation. So, for laminar flow of an oil having dynamic viscosity mu equal to 1.766 Pascal second in a 0.3 meter diameter pipe, the velocity distribution is parabolic with a maximum point velocity of 3 meter per second at the center of the pipe. Calculate the shearing stress at the pipe wall and within the fluid 50 mm from the pipe wall. Again I am repeating, for laminar flow of an oil of having dynamic viscosity mu equal to 1.766 Pascal second in a 0.3 meter diameter pipe, the velocity distribution is parabolic with a maximum point velocity of 3 meter per second at the center of the pipe. Calculate the shearing stresses at the pipe wall and within the fluid 50 mm from the pipe wall. I am also going to type in a chat box, okay? I am writing the numerical problem in the chat box. Wait, I am writing the problem in a chat box. Yes. Can you see the chat box? So this is the problem. I am giving some hints to you so that you can solve. Okay. So in this problem you have to use Heisenberg's equation, and using that equation you have to find out change in pressure del P by del X, and after that you have to use in Heisenberg's equation, and after that you have to find out the velocity V. We have known that average velocity is equation. From the average velocity equation we have to put the velocity here, and ultimately you will get the result. Today I am going to discuss a new topic which is called laminar flow around a sphere, and it is called Stokes law. First of all, calculate average velocity. Then to find out the del P by del X, then shear stress. Okay, so let me share my next screen. Let me share my screen. Okay. Can I see my note? Okay. So today we are going to discuss about laminar flow around a sphere, and ultimately we are going to discuss Stokes law. Okay, laminar flow through a fluid of infinite extent in such a manner that viscosity is the only fluid property affecting the pattern of the motion when a body moves through a fluid. It experiences a resistance which acts in the direction opposite to the motion of the body. This resistance is called drag. So drag is the resistance to flow against the body, and this drag depends on the size of the object, the velocity with which it moves, and the viscosity of the fluid. In 1815, G.G. Stokes developed one expression analytically for the resistance Fd, and it is expressed by Ft equal to 3 pi mu Vd. So this is the Stokes law, Fd equal to 3 pi mu Vd, okay, where V is the constant velocity, that means there is no acceleration in a fluid, of viscosity mu is the viscosity, and D is the sphere diameter. So this is known as Stokes law, and it is found to hold good for values of Reynolds number less than 0.2. That means this Stokes law valid for Reynolds number less than 0.2. Again, if the sphere is dropping down through the fluid under its own weight at a constant velocity v, then buoyant force plus resistance is equal to the weight. So pi by 6 d cube whole into w plus ft equal to pi by 6 d cube whole into ws, from which we can find out Ft equal to pi by 6 d cube into Ws minus W. Yes, it is drag. So drag definition is that one resistance which acts in the direction opposite to the motion of the body. This resistance is called drag. Yes. After that, if the sphere is dropping down through the fluid under its own weight at a constant velocity v, then the buoyant force plus resistance is equal to weight. Thus, pi by 6 d cube into w plus fd equal to pi by 6 d cube ws. W is the specific weight of the fluid and ws is the specific weight of the sphere. Fd is the drag force, so Fd will be pi by 6 d cube into ws minus w. This is, we can assume that we can mark this equation as equation number 2. So if you combine equation 1 and equation 2, then it will be comes out as v equal to d square divided by t mu ws minus w. We can mark that equation as equation number 3. Where v is the terminal fall velocity, which is defined as the velocity attained by a body in falling through a fluid at rest when the drag on the body is equal to submerged weight of the body. Again, the drag force Fd for any body moving with velocity v in a fluid of mass density rho may be expressed as Fd equal to CdA rho v square divided by 2. If we mark that equation as equation number 4, where Cd is the coefficient of drag, A is the projected area of body perpendicular to the flow. So remember this definition, terminal fall velocity, which is very important. Which can be defined as the velocity attained by a body in falling through a fluid at rest, and the drag force on the body is equal to the submerged weight of the body. Next, for the sphere Fd equal to 3 pi mu Vd and area pi d square divided by 4, where area of the sphere is given by pi d square divided by 4. If you put these two value in equation 4, then we'll get CD equal to 24 mu divided by rho VD. Again, we know that Reynolds number is equal to rho V divided by mu. So, in place of this, we can write RE. So, this equation becomes CD equal to 24 by RE, 24 by Reynolds number. So, this is the expression for drag coefficient for sphere on the basis of Stokes law. This is the expression for drag coefficient for sphere on the basis of Stokes law. Again, to measure the velocity, we have some viscometers. That viscometers depend on some assumptions, some principles. So these are Newton's law of viscosity, Poiseuille's equation, and Stokes law. The various methods adopted for measurement of viscosity of a fluid based on the following three principles. These are Newton's law of viscosity, Poiseuille's equation, and Stokes law. Based on these three principles, there are various types of viscometers. These are coaxial cylindrical viscometer, capillary tube viscometer, Seibel viscometer, and Rewood viscometer. So this is all about today's class. In the next class, we are going to discuss about boundary layer theories, boundary layer equation, boundary thickness, momentum thickness, how transition occurs between laminar and turbulent. Okay.